Right, this is the second video in the kinematics section. This one's on SUVAT equations. And this is basically is the kind of baseline, most fundamental class of problems in kinematics that deals with constant acceleration, and that includes zero acceleration. They're called SUVAT because obviously they're named after the letters that we use in the equations. Here we got them here. I'm going to in a moment. One thing to bear in mind is the application of SUVAT equations is we may have a problem where the acceleration is not constant because it changes throughout the problem that we're looking at, but it's we're actually applying it to each part of the problem for which the acceleration is constant. So we may well have a particle that moves with a given constant velocity and then it changes to another constant velocity. So we can apply the SUVAT equations to each part of that equation. Let's have a look at the parameters and variables first of all. To go through these. So S displacement, yeah. U initial velocity. We usually use U for initial velocity. We may not always be able to do that for various reasons. V is what we call final velocity, but it's final at the end of that phase of the problem, if you see what I mean. So we may start at initial velocity up to velocity changes up to a certain point, and then we might have another acceleration. So it's really the final velocity of that of that over that time period. Now, so you tend to use U for initial velocity. It may not always be possible. So quite often we'll have to use something else, V0, for instance, which indicates the velocity at time t equals 0. Got acceleration, of course, and time. Now, we have to be a little bit creative sometimes because otherwise things are going to get a bit confusing. We may need to distinguish between the displacement at different time points, time t equals 3. So if this sort of thing, S sub 3 would be the displacement at time t equals 3. We also may use this notation. So this is like our function notation that we've done before. So if S is a function of t, I mean, obviously it's going to be something straightforward in if the acceleration is constant, but say in general, say S is equal to t squared plus 5 or something like that, then S of 2, well, we would just substitute our 2 in for t. It'll be 2 squared plus 5, which would be 9. So sometimes S brackets 2, that would be a useful thing to use. Delta's a Greek letter. Delta S is used for change in displacement. We tend to often think in terms of the initial displacement being 0, in which case we're not really interested in the difference between the change. The change is just the displacement, isn't it? But in some situations, it may well be that we're assuming a displacement that is non-zero. So sometimes the delta S comes in useful. Initial velocity, I've already mentioned. We may need to use something other than U, because if the particular problem allocates the letter U to some quantity, it's just given to you as an algebraic quantity, then it may get confusing. I mean, sometimes, for instance, you'll have a problem where it says the initial velocity is 2u. Now, therefore, you basically got a bit of confusion between what is u. Is it the letter that we're using in the equation, and so on. So that's why we might change our notation there. And again, velocity. If velocity is a function of time, then we may wish to use this function notation. So v0 would be the velocity at time t equals 0. We could use that even if we don't evaluate it. That we could just use that as a notation. So velocity, yeah, we can use v of t or v sub t, velocity after t seconds. Delta v, of course, will be the change in velocity in the same way as the displacement. Now, we may have problems which are multi-phase. I mentioned this a moment ago, where we travel with a certain acceleration for one part of the equation and another part, and we may wish to distinguish between those two. So, and therefore, different velocities may apply. And to make a distinction between them, we perhaps use a suffix to actually denote what we're talking about. Equally, we may have problems with more than one particle. You know, two motorbikes having a race, for instance, motorbikes P and Q. So this might be a useful way to actually distinguish between them. So, you know, different problems have different requirements, and the thing is to use the idea of suffixes or function notation in order to distinguish between one and the other. Acceleration, same way, we may well have different accelerations, and time is just time, of course. But again, if we have time points that we don't know the value of, and we have, say, two of them to calculate, then we may wish to actually use a subscript for that. Okay, so those are the variables, so as far as the equations themselves are concerned, then I guess that, well, these first two are absolutely key ones. This is for displacement, and again, this is assuming that we start with a displacement of 0. So at the point where our initial velocity is measured, then the displacement will be 0 under this assumption. Otherwise, we might want to put delta s in there. So this is what it is. S equals initial velocity times t plus a half acceleration times time squared. Velocity, this is very common using this one. Velocity is the initial velocity plus the acceleration times the time. I mean, this is kind of pretty intuitive. I think if you take u from either side, v minus u equals acceleration times time, then divide by t, you'll get v minus u over t equals the acceleration, and that's what we've got down there. So that's just another form of that equation there. V equals s over t. Well, this is almost by definition, really, isn't it? This is, you know, this might be meters per second. Acceleration, well, just kind of covered that, really, haven't we? This one, displacement, is equal to the this is the average velocity, isn't it? The start and the end divided by 2, that will be the average. So the displacement is the average velocity times the time, the mean velocity, I should say, really. This last one is a bit of a mashup between these two. So if we eliminate t from these equations here, as if they were sort of simultaneous equations, then we'd end up with this one. One thing I might say as a couple of things, really. First of all, these apply whatever system of units we're using. So meters per second is absolutely the most common, but we may have problems which are kilometers an hour, or you know, or whatever, millimeters per nanosecond, whatever. Yeah, but as long as you're consistent, then that's the important thing. The other thing I just want to say, and I think I've said this before, but this is an important concept in these things. We talk about displacement. So S means displacement, but very often the questions will ask you about distance. So we need to know what the difference between distance and displacement is. Well, I think this is best illustrated. You know, if you throw a boomerang away from you, it's traveling, and it travels 100 meters away from you, and then it comes back, but it doesn't quite make it back to you. It's 25 meters short of you. Then, so it's traveled 75 back. So the total distance traveled would be 175 meters, but the actual displacement over that time period would be 25 meters, because that's where it's ended up, 25 meters from you. Now, when are they different? Well, the thing that's made that difference happen is the fact that we've got the velocity has changed sign, because when it's going outwards, it's got, let's say, positive velocity, and then it's coming back, and that we would regard that as being negative velocity. So, so if the velocity changes sign in that period of time that you're interested in, that is going to give you a difference. Okay, so the equations apply to displacement, but you may well be asked distance in the question. Okay, so that really is going through all the definitions and the equations. Let's have a look at a couple of examples. Okay, so a small stone is dropped from a high bridge and falls vertically. First of all, find the distance that the stone falls during the first 4 seconds of its motion. Right, the first thing to say here is that we have to be clear about what is positive direction, because the signs are important, I think, as I've said before. Now here, in this, basically all the motion is downwards. So it's quite reasonable, I think, just to take downwards as positive. In general, when we're looking at the kinematics problems, I would say it's more usual to actually think of a sort of a frame of reference of a little bit like your XY axes, such that down motion, it's positive going up and positive going to the right. But as long as we're consistent in what we do, then that's the important thing. But so be clear about which is positive, because otherwise you'll get one of the signs wrong. You'll have positive velocity, when you mean negative, and basically you'll get the wrong answer. Okay, so let's have a look at this now. In the normal way of solving problems with equations, and it comes in with these kinematics equations, of course. What we want to do is to write down what we know and what we don't know. And so we're looking at this. It's a small stone is dropped from a high bridge and falls vertically. Now, one of the things that crops up on all these things is that very often we've got a condition that u equals 0, and it's not explicitly said that they don't say the initial velocity is 0, but it's dropped from a high bridge and falls vertically implies. From rest is another little phrase that usually implies that the initial velocity is 0. So watch out for those, and you have to interpret them. And this is one of the challenges of a lot of these mechanics problems, really, is being able to turn these statements into kind of maths notation. So what have we got? It says find the distance. So obviously we need to find the displacement. The initial velocity is 0. The acceleration is the acceleration due to gravity, which we take as 9.8, usually 9.8 meters per second. Incidentally, that's a constant. So all these problems that involve things falling to Earth will have this. Sometimes they fall to the moon, where the gravity is much less, so the acceleration is much less. But anyway, that's in this case we've got A equals 9.8, and of course this is positive because our frame of reference is downwards for positive, which, of course, if it's not, then we may well have, if we're actually taking frame of reference as positive, it's upwards, then the acceleration, if it was acceleration due to gravity, would be minus 9.8. Okay, and we're told first 4 seconds of its life, that means t equals 4. So we've got 3 things we know and 1 thing we don't know. I mean, when we look at all these things, this is a shoe-in for s equals ut plus a half at squared. So we can just substitute all those different things into that equation and just work it through for s. And that gives us 78.4 meters. Now, displacement, but of course, during the course of this motion, we've not had any negative, or there's not changed sign. The velocity has not changed sign, so we can take that as being the distance as well. The second part of the question, find the speed of the stone when it has been falling for 4 seconds. So again, this is the final velocity that we're interested in. The initial velocity is still 0, A still 9.8, D is still 4. So again, this looks tailor-made for this equation here. You can just sub in these things. We don't even have to change the subject of the formula, really. It's just like before. It's actually explicit in V already. Work that through, and that gives us 39.2 meters per second. That's the speed. And incidentally, because V, what we've got is 39.2 meters per second downwards is the velocity. The speed is just a scalar, so it's just a question of the size of the velocity, and the size of a velocity that is 39.2 in the downwards direction is just 39.2 meters per second. So that's the difference between speed and velocity. Right, so that's that one. And let's just have a look at this one. Slightly more complicated, but not too difficult, I don't think. A lorry is moving along a straight horizontal road with constant acceleration. The lorry passes a point A with speed u. So this is an example where kind of u has been hijacked, if you like, for the purpose of the question. As it turns out, it means the same thing, but anyway. And u is less than 34, and 34 seconds later, it passes point B with speed 34. Given that that distance is 240 meters, find the value of u. Okay, so what we're saying, the initial velocity is equal to u. Time is 10 seconds. Strip that out of the problem. The velocity, I've used suffix b here, is 34, and the distance is 240 meters. So when we look at these and go back to our kinematics equations, it does look like this one is the one that features all our stuff. Obviously, we need to find u. So there's a kind of question mark above that one. So yeah, displacement is equal to the average velocity over that period times t. 240 equals, well, we don't know this, still have to put this in algebraically, plus 34 over 2 times 10, and then solve for u. And that's what gives us that u equals 14. Okay. Right, so that is that one. The time taken for the lorry to move from A to the midpoint of AB, well, the midpoint of AB would be 120 meters from A. Now, u is going to be greater than 0 since the acceleration is constant throughout. So I think that implies that we can assume that we're starting off with a positive velocity. So therefore, it doesn't change. It doesn't change direction. The sign doesn't change, and the lorry is going in the same direction all the time. Okay, so right. So we said the midpoint's 120 meters from A. So what we've got here, we don't know A, we don't know S, so 120. 14 for the initial velocity, because that's what we worked out here. The time we don't know. So if we just look at those together, we've got 2 unknowns. We might need something else. Well, we've got something else, which is the velocity equals 34. Now we want to know A. So we could, we could, well, we want to know T, I should say, I beg your pardon. So what are we going to do? We could probably do this, but I've done it this way anyway. I've basically said, let's find the acceleration. So I've gone off into this little panel here, and we've used this equation here, V, U, A, S. That's four things, one of which we don't know. V equals V squared equals U squared plus 2AS. So we just substitute what we know into there. Obviously, A is the only thing that's left. And we have to rearrange and solve for A, and that's going to give us A equals 2 meters per second. So, so I can plug that into there. Now I could have, we probably could have done it a different way there, but I just wanted to illustrate using this equation. So what have we got? A equals 2, S equals 120, U equals 14, T we don't know, so we can bang in this equation here, S equals UT plus a half AT squared. And yeah, if we substitute what we know into there, then what we end up is we actually end up with a quadratic in T. So we need to factorize that, and that's T plus 20 into T minus 6 equals 0. It's going to give us T equals 6 or minus 20. So, so in the context of this question, then the time taken would be 6 seconds, because minus 20 is before the scope of the problem. Now, in other situations, it may be relevant. Just because it's negative, it doesn't necessarily mean it's not relevant in all situations. T equals 0 is just a reference point in time. So time does exist before T equals 0 in your problem. So it may well be that it is relevant in some circumstances to have a negative value of T. Got to look at the problem and see whether or not that makes sense. But okay. But in this question, basically, yeah, it's just T equals 6 seconds is our solution. Okay, so that's basically it. That's kind of a couple of illustrations of how we use the SUVAT equations. There's one or two other things we want to bear in mind, and things that come up, which we'll be covering in later videos. But hopefully that has been useful, and you'll be able to tackle quite a lot of these problems now. So, okay, right, well, I shall see you in the next video.